Here. My name is Jakub, and this is a rehash of a talk I delivered at KubeCon Delhi. So what I changed is mostly the color scheme. So now it's blue. Used to be purple. And today we will talk about fuzzing. But before that, I do have an ad to make. So it turns out we are hiring. AlphaSense is looking for a good engineering manager for our Kubernetes team. So if you have experience architecting, implementing, and operating Kubernetes at scale, and you are good with people, scan this, and I promise you will not regret it. It's a really nice team. Not my team, by the way, but nice team. A little bit about me. I'm Jakub. I come from a country very far away. I came from Sweden. How did you know that? Right, you live there. My day job is about crossplane, so I run a team handling crossplane internally. But besides that, I'm interested in compilers, performance optimization, and cybersecurity. And this talk will include all of those topics. So what you will get out of this talk is learn more about the CVE process, learn what fuzzing is, and hopefully I can make some of you be encouraged to contribute. So first things first, CVE 2024-26147. This was a high severity denial of service vulnerability I discovered in Helm last year. It was a CVE 457, use of an uninitialized variable. And when I reported this, it was really two different vulnerabilities, and I reported it at 2 different days. But since the Helm maintainers decided the root cause is the same, they actually released a single CVE. So the first part affected the repository subsystem of Helm. And every Helm repository allows you to define metadata. And on the left side, you see the healthy, normal metadata file. And on the right side, you see the malicious index that would cause a program termination if it was to parse it. Similarly, and the root cause is that the metadata was missing. The fix was that we check if the metadata is missing. If it's missing, we zero initialize it. The second part affected the plugin subsystem. And I was quite surprised because I didn't know Helm has plugins until I found this. But it's a really nice feature. There are many great plugins you can use. And the story is similar. On the left side, you see the healthy, normal plugin metadata, and on the right side you see a malicious version of the metadata. And you are correct, it's literally an empty file, so that was interesting. And the fix is similar. We check if the metadata is nil. If it's nil, we zero initialize it. The root cause is that metadata is pointer, and Go being the memory safe language it is, if you try to dereference a nil pointer, it will terminate the program to protect you against weird stuff. For those of you that have never seen a CVE get patched in an open source project, interestingly, when that happens, the commit oftentimes isn't very revealing. It kind of looks weird. There is no context to it. And why is that? Well, the reason is quite simple. If you want to announce a CVE, if you want people to patch the program, first you have to build a new version of the program, right? So you want to fix it in a low-key way. So if you ever do see a weird commit in an open source project with no tickets, no extra information, it's very likely you are witnessing someone patching a security problem. So I was curious what kind of impact this had in the ecosystem, and I looked at the identifier on Git, and there was around 750 pull requests mentioning the CVE in various projects like Argo CD, Flux CD, Tri-V, K9S, what have you. There were some commercial products affected. So Google released security releases for GKE on-prem and classified this as a high severity container vulnerability. Red Hat released several RHCAs, including RHCAs in OpenShift, and classified them as important. So there was some impact in the ecosystem. So what is it really? It's 2 different vulnerabilities. And I will try to present them now. Hopefully stuff explodes, right? That is the goal, to make it fail. And locally, I do have an older pre-patch version of Helm. So I will present the first vulnerability, crashing Helm. I prepared a malicious Helm repository using Google Cloud Storage. And we'll see when I try to add it, we get a beautiful stack trace. And you might think, so what? Helm is a CLI tool, right? I can just run any other command, right? Stuff keeps working. Well, the thing is that Helm is really two different projects. It's both the CLI, but it's also the SDK. And hundreds of other projects like Argo CD, Flux CD, what have you, embedded. So it turns out if you were able to make that program embedding Helm SDK interact with a malicious repository, you could trigger a runtime panic and basically disable the service embedding it. So I think that was interesting. The second part I think is much more interesting to me. So Helm has plugins, as we all know. So let's see what happens if I try to install a plugin I prepared. We get a stack trace, a panic, and you might think, so what? This is a CLI tool, right? I can just run other commands. So let me try to run other commands. It panicked again. What's happening? Let's try something simpler, a Helm version which literally prints a string. It panicked again. So it turns out that even though installation failed, the malicious metadata file was inserted into your local file system. And what Helm does on every invocation, you don't see it because it happens very fast. It will actually look over the local file system, inspect the metadata, and as it's trying to parse it, it encounters that null pointer dereference. So it means if you were able to trick someone into installing this plugin, you could basically brick their Helm, which was kind of interesting. But how do you think I found this? A, did I mess up copy-pasting YAML? B, was I reading the code? C, did I call a friend who knows this kind of stuff? A, B, or C?
A.
None of the above.
No, D. Yes, you guessed. No one guessed besides that. So it was D. It was a result of a targeted fuzzing effort. But before that, really, it's cool to have a CV in a very popular cloud-native software. It's a bragging point almost. You can put it on your CV, right? It's nice, but it wasn't really a very impactful vulnerability. You couldn't cause a lot of damage. You couldn't gain access to systems. But let's look at some other vulnerabilities. How many of you heard about Heartbleed? Quite many. Shell shock? Yes. More recent example, WannaCry, Eternal Blue, huge economical damage, airports shut down, hospitals shut down. Why am I talking about those three? What's common amongst them besides the fact that they were important? Well, it turns out that all of them were discovered using automated techniques like fuzzing, symbolic execution, or concolic execution. And it's a bit of a secret in the industry that many, perhaps most real high-severity vulnerabilities get discovered using automated techniques, of which fuzzing is the most popular one. And you will not see that in the vulnerability descriptions. The CVEs don't state it, but frequently that is how they are discovered. So what is fuzzing? How many of you know what fuzzing is? Some people know already. Well, it's really a simple technique. You generate huge amounts of data, you feed it to your program or parts of your program, and you see what happens. Like, that's all it is. Some fuzzers, like the Go standard library fuzzer I used to discover this, are a bit smarter than that. Not only will they generate data, not only will they execute it, but they are also aware how your program executes. So using that information, they can change the way they produce data and discover new paths quicker. But before that, I prepared a small workshop. I know not all of you are programmers, and not all of you are Go programmers, but hopefully there are some in the audience. So let's look at some bugs. So, can someone tell me the value of n that makes this program panic? 3, right? Any other values? -1. Right. So it turns out in Go, like in many other languages, we count array elements from 0. So A is 0, B is 1, C is 2. If you tell it to access character position 3, that's technically character number 4. It doesn't exist. And we get a panic. And the same story happens when you try a negative index. That was easy, though at KubeCon India, people were faster at guessing this. So you should try harder next time. Let's look at another bag. Can you tell me a string that makes this one panic? Well, the answer is x85, x85. You cannot see this. Well, it turns out it's quite hard for humans to figure this stuff out. But if you pointed the Go standard library fuzzer at this function, it would discover it in less than a second. So this technique is more powerful than humans. So that's very cool. And this is from Go standard library, a time parsing library. So this had a CVE. This was a real vulnerability. And the fuzzer finds it in 1 second. And it used to be the case that using fuzzers was very hard. It required you to have a lot of domain knowledge. You had to know how to use them. But Go implements it in a very simple way. So to discover that vulnerability, you just had to run those 5 lines, and it would find it for you in 1 second. So let's do some fuzzing. We will start with the simpler case, the plugin vulnerability. And when I run this, the Go will start generating data and feeding it to our target. Immediately, we do see a stack trace, and what ends up happening is Go will save the failing input into your local file system so you can actually inspect it, see what caused it. So this is how I found the plugin vulnerability. The first one is a bit harder because if you recall, the structure of the triggering input was structured. It wasn't an empty file. So it turns out the fuzzer has to discover that YAML structure, okay? And it turns out that on my machine, if I were to start from 0, it takes approximately 3 hours for it to discover the conditionals leading to that path. So in the interest of time, I will spare you that, right? We will not wait 3 hours. I prepared a version of it that hard codes the failing input just for demonstration purposes. So if I run this one, we get the stack trace. So that's basically it. Was it hard? Did I have to do a lot of stuff? No, I just had to use the tool. It did all the work for me. What's in it for you? Well, there's really 3 paths. First of all, obviously, you can use it in your internal projects. You can embed it in your CI/CD systems, right? You can make the fuzzer run for, let's say, 1 minute per commit. And given the random probabilistic nature of fuzzers, it has a chance of uncovering new code paths, maybe security vulnerabilities, maybe stability issues. So it can boost the stability of your systems. So it's quite nice. The second part is fuzzing open source projects like I did with Helm, right? There's likely hundreds of bugs waiting to be discovered in Helm, Kubernetes, Crossplane, Argo CD, yada, yada. You can try to do that. You can try to find vulnerabilities or stability issues. If you find them, report them to maintainers, and you can help the ecosystem be more stable, right? And the third path, which is the most interesting to me, is improving the base fuzzing technology. But before that, maybe let's look how fuzzing works at a lower level. So when I ask you how does a program look like, what do you imagine? Lines of code, right? We are thinking about lines of code. The thing is, if you had a compiler engineering course in university, or you were interested in compilers, this is yet another representation of the very same program in the CFG, control flow graph, in the static single assignment form. So this is the same program. And if you look sideways and kind of squint, it kind of looks like a banana. I want you to remember that because it's very important. The thing is that that function is very simple. the control flow can get very complex. This function is slightly more complex. There are functions that are 100 times or more complex than this one. And because we have conditional blocks, because we have loops, it turns out if you try to trace the amount of unique paths this program can take, it's at least a few thousands, and it would take you a long time to find them. So what fuzzers do, they automatically try to discover all the paths for you. So let's do some manual fuzzing. We will use this fuzzer, Jakub V1. I'm a manual fuzzer. We have our toy function. We will keep passing it inputs, okay? So the first input is not 5 letters. On line 4, we have a conditional that checks the length of the string. Obviously, it's not 5, so we go from line 4 to line 21. And in the SSA form, we go from the block B1 to B2. We didn't cover much of the function. Let's pass more. Bliss. This time, the string is 5 characters long, so we take the first conditional. But we fail on line 5, and we take this return because B is not C, okay? And in the SSA form, we went from B1 to B6 to B5. So let's do more. Charm, we covered 4 blocks. Crisp, we covered 5 blocks. Crave, we covered 6 blocks. Crush. We didn't get a panic. Why didn't we get a panic? Big H, right? Because your CPU, when it analyzes strings, it doesn't see letters. It sees numbers, integers. And an uppercase H and a lowercase h is a completely different number. So we take this branch here. We don't reach the panic. But let's see what happens when we pass a lowercase h. It turns out we went from B1 to B6, B10, B14, B18, B22 to B20 to a special type of a block, exit block. This is what a panic compiles into in Go. And we basically found a security vulnerability in our wonderful program. Was it hard? No. This is what fuzzers do, right? They do it for you. A little bit of a deeper dive, a bit of a trivia. The Go compiler and Shrek are both like onions. They have layers. So on the left side, you do have the vanilla code we have. And then you have the optimization onion, several layers that lower your code, optimize it, refine it for greater performance. And in the end, you end up with raw assembly. In this case, AMD 64, that your program, your computer will actually execute. Why am I talking about this? Well, it turns out that a bit of magic is happening here, because when you fuzz in Go, Go doesn't compile your function the same way. If you compile it the same way, the normal way, on the left side, you see the structure we will get. But if you fuzz, the structure isn't like a banana anymore. It's more like a Christmas tree. And why is that? Because Go inserts coverage blocks. It needs to know which part of the function it's executing, okay? So we get additional control flow. The function becomes more complex. And in the assembly, we get some extra instructions. So on the left side, you have the vanilla normal compiled version. On the right side, you have the instrumented version, and we get some conditionals, some memory load, some increments, and a bit of a branching. This is how Go knows what it's executing, okay? This is the magic. Here I had a 5-minute long section about the high-level architecture of the fuzzer, but when I was delivering it in Delhi, half of the audience fell asleep. So I will skip this. We also have 5 minutes less, okay? One thing that is important to cover, we have this concept of mutation. So Go ships with several mutators that, given an input, mangle it a bit to discover new strings to execute or different data types. And you have several simple transformations, like removal of random bytes or insertion of random bytes, swapping bytes. Why am I talking about it? When the Go fuzzer was released, it generated a large amount of buzz in the industry. There were blog posts, there were social media posts. But if you look at the Go version control over the last year, there's only a single maintainer working on it. And this is an open source project. You can contribute, right? And you might think, how do you contribute to something as arcane as a fuzzer? Well, you work on it the same way you work on any other software. So you fix bugs, you implement new features, or something that I'm most interested in, optimize performance. So it turns out I did some of that, and if you recall, we ended up with more complex control flow. And the reason is the Go fuzzer uses a counter strategy called never zero. They adapted from the AFL fuzzer. What it means, we basically, when we increment a counter, which can take an 8-bit value, when we are about to overflow from 255 to 0, we don't go to 0, we go to 1. And that boosts performance. The fuzzer can find more stuff quicker. The thing is, if you care about performance, CPUs really don't like branching, okay? If you have if statements, you automatically split your program state into 2 different paths, and CPUs have to guess which path do we take. So I looked at this and I thought, what if we made this branchless? So to do that, I basically used some arithmetic and some shifting, and you can express the same logic using this branchless never zero. And the biggest benefit of it is that our beautiful banana remains the beautiful banana, okay? That's the main one. The second one is we got a 2% performance gain. Maybe it's not much, but you know, this project is used by hundreds of people to discover vulnerabilities. If you can make their work 2% faster, it has a big impact, right? You can help the community. Less electricity gets used, so there are some benefits. So that's cool. Now let's look at something else. It turns out that every time the fuzzer executes inputs, we report back the coverage. So we snapshot the coverage for every single basic block. And when we do that, we round down the value to the nearest power of 2. And the Google engineer that implemented this used a very awesome bitwise trick. So if you pipe any 8-bit value through this, you will get the rounded down version. But I looked at this and I thought, you know what? When you were in middle school and your teacher asked you how much is 5 times 9, were you counting on your fingers? No. Some of you did, but not most of us didn't. So I thought, you know what? What if you pre-computed all the answers ahead of time and just looked them up? So I did just that. And the result is 18% performance gain, which is cool. This optimization was significantly easier to implement, right? I didn't have to touch the compiler. I didn't have to work with SSA. But the benefit is much bigger. So it turns out if you combine those 2 optimizations, you end up with 20% higher performance. So the fuzzer will be 20% better at finding vulnerabilities. We will use less electricity. It has a good karmic impact. And since I delivered this talk, I'm happy to announce this was actually merged into Go, so you will get this in Go 125. So if you are wondering why is the fuzzer slightly faster, the reason is because of that, okay? To end, I want you to know that fuzzing isn't limited to Go. There are fuzzers for Java, Python, JavaScript, C++, C#. There are black box fuzzers that you can use to fuzz binaries. You can fuzz all kinds of software, customer-facing APIs, mission-critical systems, business applications. You can find different classes of vulnerabilities like SQL injections, denial of service. You can apply something called differential fuzzing. If you work on algorithms doing, for example, lossless compression, you can make fuzzer generate inputs, then decompress them and compare whether they were equal. It allows you to find logic bugs in various algorithms. So I think that is kind of cool. That's all I had for you today. Feel free to add me on LinkedIn, check me out on GitHub. And if you do have any questions, just email me, okay? And we are hiring also, right? Thank you. Any questions?
We have time for questions, so if you have any questions, please go ahead.
Just a quick one. I know you mentioned open source and spending time on your free hours to go on test. But why did you choose Helm? What were you doing when you actually?
Because when I joined AlphaSense, for context, Oscar used to be my manager, and he quit the day after I joined. The first task I got was to implement Helm JSON schema, and this was absolutely the most boring thing I could do. So I started fuzzing Helm out of frustration, and I discovered the CVE, so in the end it worked out for me. Yeah. Yes?
So how would you recommend to add fuzzing to your pipeline as unit, like on a unit test
So,
level or a smoke test?
you fuzz parts of your program that take input, okay? So anything that can take simple data types, Go doesn't support fuzzing complex data types. So you cannot pass structs, but you can pass strings, bytes, and so you take a function, maybe high-level function, you write a fuzz test, and then you add a pipeline stage that says, hey, fuzz it for me for 1 minute, for example, right? And given the random nature of fuzzer, it has a chance of finding something. Yes? Yes?
How would you define what you will fuzz and what you will just unit test? Like, some people could have catched that with better unit test testing the same things that the third person was saying inside the program.
Can you repeat the question in the mic?
Right. I forgot his question. Could you?
No, it's
Yeah, so the question is, how would you split what you do with fuzzing and what you do with just better unit testing of functionality? Because some people like testing a string or a size of string, they would have done that with just unit testing.
Okay, so the question is, how would you decide whether to unit test or fuzz test a piece of code? I think, where fuzzing shines as sometimes you get bugs that are not obvious for a human. Like if you try to write a unit test for that Go standard library bug where you have to come up with those weird switchers, like how are you going to think about it? Hey, let me try that. No, it's not evident from the code structure. So it's good because you can just point it at something and it can find bugs, right? And if you ask me what are the best targets, functions that panic or functions that access arrays using index arithmetic, that is prime target for fuzzing. Or stuff handling parsing YAML or JSON or whatever, like highly complex functions, I would say. Yeah. One more, please.
okay, I think that was it.
Okay,
Thank you so much.
thank you.